Good morning, class. We are looking at Module 3 that covers Chapter 6 and 7. Chapter 6, Normal Probability Distributions. Here's the rest of it, the second half. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What percentage of people has an IQ score above 120? It's important to understand in stats, we mainly deal with word problems. So what is the given symbolically? We are dealing with a normal distribution with a mean of 100. Mu is 100, sigma is 15. So that's the first thing we need to write. And what percentage would have IQ score of above 120? We are interested in probability of X larger than 120. So we are going to change the X to Z using the formula Z equals X minus mu over sigma, where mu and sigma, we made a note of it, and X is 120, resulting in 1.33. So this is a normal distribution, equals probability of Z larger than 1.33. This is standard normal distribution. Here's a graph of a normal distribution, and Z must be larger than or equal to 1.33. So you locate it between 1 and 2, and this is what you want. This is the area of interest. The reason it's important to have the graph, it gives you an idea. As you know, each side is 0.5. The total probability is 1, so it's something definitely less than 0.5. And you can use technology or table. You come up with the answer of 0.0918. Because the question was asking for a percentage, we change it accordingly. What is the maximum IQ score for the bottom 30%? So we need to understand the concept. For this graph, they want the bottom 30%. So this is the bottom 30%. The area to the left is 0.3. We need the Z-score. So you look up the Z-score either from the graph, the table, or you use technology, either way. So from the Z table, it's somewhere between the two numbers. And as you recall, Z is X minus mu over sigma. If you do the cross product and move the mu, this results in X being equal to mu plus Z sigma. So replace the mu with 100, Z with a number between the two, negative 0.525, and sigma with 15, and it gives you 92.125. So the maximum IQ score for the bottom 30% is 92.125. Clearly must be less than mu because it's less than 0.5. That's why. If it was precisely 0.5, that would be the mu, which would make it 100. Now, if we want to use technology, we use inverse norm. Area to the left is, you have to write the area. I hope you remember that, 0.3. You can even write mu is 100, sigma is 15 without changing the numbers accordingly. And it gives you the answer, which of course is more precise than what we have here. The reason why this Z-score comes from the table is not as accurate as the Z-score that is used with technology. However, it's pretty close. 92.125 is our calculation, 92.133, or let's say 92.13, and change this to 4 if you want, is the answer from technology. So pretty close. Men have head breadths that are normally distributed with a mean of 6.0 inches and a standard deviation of 1.0 inches. If a man is randomly selected, find the probability that his head breadth is less than 6.2 inches. So, what is given? ND, normal distribution. Mu, the mean is 6, and sigma, or standard deviation, is 1. So that's the given. We want the probability of x less than 6.2. And the key is that n is 1. Therefore, we use the z-score of x minus mu over sigma. We have mu and sigma, and x is this number, 6.2. And that's your answer. So probability of x less than 6.2 is the same as probability of z less than 0.2, using S and D being able to read from the table. That's why. So you look at 0.2, it's somewhere between 0 and 1. That's the area we need, and we can pick up the answer from the table. If 100 men are randomly selected, find the probability that their head breadth mean is less than 6.2 inches. I want you to compare and contrast part A and B. In part A, you're dealing with one subject, 1. Now, you're dealing with 100. Anytime the number is more than 1, instead of writing probability of x, in this case less than 6.2, we are going to write probability of x bar, yx bar, because it's more than 1. And so with n being 100, the formula we use is x bar minus mu of x bar over sigma of x bar, where mu of x bar is equal to mu, sigma of x bar equals sigma, known as the central limit theorem. We discuss that in a moment. So mu of x bar is mu, the same value that we have here. Sigma of x bar is sigma over square root of n. Oh, how come it's sigma over square root of n. Sigma of x bar is sigma over square root of n. So (6.2) minus 6.0 over 1 over square root of 100, which makes it 1 over 10. In other words, this gets in essence multiplied by 10, becomes 2. So probability of z less than 2. So you locate the 2 here. And we want this area. And from the table, we read 0.9772, which is a lot higher than the number here, because you're dealing with 100 men. So it gets closer and closer to the actual mean that is expected. And so with that being the case, let's look at the technology. So normal CDF, the lower value, they pick this number. I hope you remember I said for the lower value, you can even use 1,000, even 100. Now this means -1, E99, that's exponential, that's a scientific notation. That means times 10 to the power of 99. That means -1 with 99 zeros. The upper value is 6.2, and mu is 6 with sigma being 1. and look at the answer. This is the answer from technology. This is the answer from the table. They're practically the same if you look at the fourth decimal. So 1, 2, 3, 4. This number will change to 3 because next to it is 5. So it's pretty close. Now, in this case, everything is the same, mu is the same, but sigma, which was 1, we have to divide it by square root of n or square root of 100, or in essence, and now sigma of x bar is 1 over 10. See, 1 over 100 to the power of 0.5, that means 1 over 10. And look at the answer. Here's your answer from technology. Here's your answer from the table. And again, if you go with 1, 2, 3, 4 decimals, 1, 2, 3, 4, they're pretty much the same. Again, as far as the number of decimals, you always pay attention to what they ask you to do. The assets in billions of dollars of the 4 wealthiest people in a particular country are as follows: 33, 29, 16, and 11 billion dollars. Assume that samples of size n equals 2 are randomly selected with replacement from this population of 4 values. After identifying the 16, the way you come up with 16 is 2 to the power of 4. Different possible samples, and finding the mean of each sample, construct a table corresponding to the sampling distribution of the sample means. So what it means is this. We're going to pick 2 from here. And when we say with replacement, that means 33 with itself, and 33 with 29, 33 with 16, 33 with 11. 29 with itself, with 33, with 16, with 11, and all the way to the end. So you get something like this. Again, if you look at the very first number and first number only, 33 with itself, the average is 33. 33 and 29, add them up, divide by 2, 31. 33 and 16, add them up, divide by 2, 24.5. 33 and the last one, 11. Add them up, divide by 2 is 22. For each one of them, there is one possibility out of 16. But for this one, all of them are 1 out of 16. So for some of them, it gets repeated because 33 and 29, they result in the same as 29 and 33. So here's what we write one by one. This has to be continued all the way to the end. But when we want to wrap it up, we write when x bar is 33, there's only one outcome out of 60. When it's 31, there are 2 outcomes. So take a look at what happens. If you look at this one, there's only one outcome. But if you look at this 2, 33 and 29 versus 29 and 33, they result in the same x bar, which is 31. So it's 2 out of 16. And I didn't want to simplify it on purpose. We all know this is 1 over 8. So if you want to answer it as the final answer, this is 1 over 8. Let me write that. But I wanted just to make a point that when you pick a number with itself, there's only one way. But with any other number, there are 2 ways. That's why some of them are 2 out of 16. Most of them are 1 out of 16. This table is the sampling distribution of the sample means. What sample? Sample of size n equals 2. Because we pick 2 out of 4. Now here's the important thing. Compare the mean of the population to the mean of the sampling distribution. The mean of the population, it's very simple. Add them up, divide by size, which is 4. Mu equals summation of x over n. Pay attention to the notation. Mu, the Greek letter, and capital N for the population. Add them up, divide by 4. $22.25 billion is the average. As you recall, if you want to calculate the average here, is the summation of X bar. Remember, summation of X P of X, this would be summation of X bar P of X bar. So multiply these two numbers, these two numbers, these two numbers all the way to the end and add them up. So 33 times 1 over 16, 31 times 2 over 16, all the way to the end. Again, on purpose, I'm keeping it as 2 over 16. So the answer is 22.25. As you can see, mu, and this is mu of X bar. Why is this called mu of X bar? Because we are calculating the average for X bar. How do you calculate the average for X bar? Add them up, divide by the total size, which is 16. That's why that 1 over 16 or 2 over 16 comes about. And as you can see, do the sample means target the value of the population mean? They are identical. In general, do sample means make good estimates of population means? Why or why not? The answer is absolutely. The sample means target the value of the population mean. That is the mean of the sample means, the mean of the sample means. So if you take the average of this, as long as you have all those samples, or the expected value of the sample mean is equal to the population mean, mu of X bar equals mu. The population of current statistics students has ages with mean, mu, and standard deviation sigma. Samples of statistics students are randomly selected so that there are exactly 44 students in each sample. For each sample, the mean age is computed. What does the CLT, central limit theorem, tell us about the distribution of those mean ages? So let's discuss the concept first. The central limit theorem, a sampling distribution of sample means is a distribution obtained by using the means computed from random samples of a specific size. If you recall in the previous case, the size we chose was 2. Because if it gets larger, it's very easy, very hard to do it by hand. Taken from a population. So a sampling distribution of sample means is a distribution obtained by using the means computed from a random sample of sample size taken from a population. Again, we did 2 out of 4 from the previous, on the previous page. For samples of size n larger than or equal to 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. The approximation becomes closer to a normal distribution as the sample size n becomes larger. So here's the conclusion. The distribution of sample X bar will, as the sample size increases, approach a normal distribution. The mean of the sample means is the population mean. So mu of X bar equals mu. The standard deviation of all sample means is sigma of X bar equals sigma over square root of n. So in this example, so this was a background. Now for this question, remember, n is 44 and it's larger than 30. A sampling distribution of the mean ages can be approximated by normal distribution with the mean mu of X bar equals mu and standard deviation sigma of X bar is sigma over square root of n, which makes it sigma over square root of 44 for this question. A boat capsized and sank in a lake. Based on an assumption of a mean weight of 137 pounds, the boat was rated to carry 50 passengers. So the load limit was 137 times 50, which is 6,850 pounds. After the boat sank, the assumed mean weight for similar boats was changed. And that's the idea, from the assumption of 137, which was wrong, to something else, which happened to be 170 pounds. That's the background. So what's the question? Assume that a similar boat is loaded with 50 passengers. And assume that the weights of the people are normally distributed with a mean of 174.1 pounds and a standard deviation of 35.1 pounds. Find the probability that the boat is overloaded because the 50 passengers have a mean weight greater than 137 pounds. Okay, so it's a word problem. What is given? You're dealing with a normal distribution. We are dealing with normal distribution. N is 50. The mean, mu, write them symbolically, is 174.1. Standard deviation, sigma, is 35.1 because it pertains to the population. And for this one, probability, remember, N is 50. So probability of X bar larger than 137. That's what we are calculating. Z equals X bar minus mu of X bar over sigma of X bar. Instead of X bar, we put 137. Instead of mu of X bar, we put mu, which is 174.1. And instead of sigma of X bar, we put sigma divided by square root of 50. Sigma, which is 35.1, divided by square root of n or 50. This will result in this number, negative 7.474, meaning probability of X bar larger than 137 is the same as probability of Z larger than negative 7.474. This is a normal distribution. This is SND, standard normal distribution. So we can look at the table. And I highly recommend you go with the graph. So we have this, and this number here is this number, negative 7.474, as you can see. And as you recall, when we start from the mean, we go 3 standard deviations on both sides. It covers 99.7%. So this is way to the left of number negative 3, negative 7.474. That's almost 100%. You can even use a calculator. Gives you a number very close to that. The boat was later rated to carry only 15 passengers, and the load limit was changed to 2550 pounds. In other words, 170 times 15. Find the probability that the boat is overloaded because the mean weight of the passengers is greater than 170, so that their total weight is greater than the maximum capacity of 2550. That's really the concept. And so we are again dealing with normal distribution, but now N is what? 15. The mean mu is different now. We have the same mean, 174.1, and sigma is 35.1. But this one, probability of X bar, is larger than 170 now. This one is for that. So the only thing has changed from here is the value of N, and this, instead of 137, we're going to go with 170. All right, let's calculate the Z again using the same formula as this one, except X bar is 170 and N is 50. So 170 minus 174.1 over 35.1 divided by square root of N, which is 15, resulting in this number. So here's normal distribution. Here's the standard normal distribution, P of Z larger than negative 0.4524. And you can see that this is different than that. If we were to graph this, I'm going to graph it. It will look something like this, class. This number is here. We want this area. That's the idea. And you look up the table, the area to the left subtracted from 1, you use technology, whatever. Do the new ratings appear to be safe when the boat is loaded with 15 passengers? No, because there's a high probability of overload. This is very high. The new rating do not appear to be safe when the boat is loaded with 15 passengers. The probability is 67.45% that is overloaded. So that's not a good rating. At an airport, passengers arriving at the security checkpoint have waiting time that are uniformly distributed between 0 and 10 minutes. All of the different possible waiting times are equally likely. That's why it's called uniform. Find the probability that the randomly selected passenger has a waiting time of at least 7 minutes. All right, let's define a couple of things. Uniform distribution. It's a continuous random variable. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. Properties of uniform distribution. Density curve. The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1, because the total probability is 1. Because the total area under the density curve is equal to 1, there's a correspondence between area and probability. Therefore, probabilities can be found by identifying the corresponding areas in the graph using this formula for the area of a rectangle. Area equals height times the width. What do we mean by that? In this case, the total area under the curve must be 1. And we know the width is from 0 to 10. The width is 10. And the height must be 1 over the width, 1 over the 10. So if the width is 10, the height must be 0.1. So here's the height 0.1, here's the width 10. This total area, this rectangle has a total area of 1, and it is a uniform distribution. Probability of wait time of at least 7 minutes. That means find the probability of X larger than or equal to 7. So you locate the 7, and this area is of interest to us, which means the height, which is fixed at 0.1, times the width of this shaded region. What is the width of this shaded region? 10 minus 7. 10 minus 7 is 3. So again, we want to go from 7 to 10. So the product, 0.1 times 3 is 0.3. So there is a 0.3 or 30% chance that a randomly selected passenger has a waiting time of at least 7 minutes. Number 12, information regarding standardized tests used for college admittance. Scores on the SAT test are normally distributed with a mean of 984 and a standard deviation of 204. Scores on ACT tests are normally distributed with a mean of 20.7 and a standard deviation of 4.3. So those are pieces of information. It is assumed that the two tests measure the same aptitude, but use different scales. If a student gets an SAT score that is the 65 percentile, find the actual SAT score, and they are telling us to go with the whole number. They are telling us how to round it. So first, what is given? For SAT, which is ND, normal distribution, mu is 984, sigma is 204. For ACT, which is again normally distributed, mu is 20.7, sigma is 4.3. That's understanding the given. So what is the process here? We want the 65 percentile. So in this case, it's a normal distribution. This is right in between. This blue line, you locate this area is 0.65. So this area is 0.65, and we need this point, it's Z score. So area to the left is 0.65. Why? Because they said so. We need to find the Z value. And find the X value. So we find the Z from the table, from the technology, and then we calculate the X value. How? Z is X minus mu over sigma, therefore X is mu plus Z sigma. We are going to use this formula. And because it's SAT, mu and sigma come from here. All you need, come up with the Z value either from the table or technology. So what are we using? We are using mu equals 984, sigma equals 204. Why? Because they said it's SAT. Now we're going to use technology. Inverse norm with the area of 0.65 mu 0 sigma equals 1 results in this number as the Z score. So mu is replaced by 984, sigma by 204, and Z with this number, you can stop at some point. For example, if I go with the fourth one, that doesn't change, remains at 3. And this is the answer because they said the whole number. The answer is rounded accordingly. 1062. Look at this number next to the 6 goes up to 3. So you do it accordingly. What would be the equivalent ACT score for the student? And they want 1 decimal now. And that's something you want to pay attention to. 1 decimal, whole number, so on and so forth. So that's extremely important to see what they are asking you to do. Come up with the exact answer. Okay, we are going to use the same Z. We have already come up with the Z score here. And we're going to use the same formula, X is mu plus Z sigma. However, the mu and sigma come from here. That's the bottom line. So we are going to use the Z score that we found here. And we want the ACTX. We use the same formula. However, mu is 20.7. Sigma is 4.3. Plug in. 20.7 plus the same Z score from the previous one times sigma of 4.3 results in this one. Then they say 1 decimal. So we're going to stop here. Next to 3 is 6. We change it to 4. The answer is 22.4. 22.4. If a student gets SAT score of 1494, find the equivalent ACT score, and again, they want one decimal for the ACT. So SAT is given, ACT is missing. How do you find that? From SAT score, which is the X score, we will need the Z score. We want to see what this corresponds to as far as the Z score is concerned. And then from the Z score here, we go to the X for ACT. That's the process. So SAT X score of 1494 gives us the Z somehow from the table. We find it using the formula, and then we go to the X value for ACT. Z is X minus mu over sigma. And for SAT, of course, X is given 1494. Mu and sigma for SAT are those, resulting in 2.5. So that means for them to be identical, they both must have the same Z-score of 2.5. So if the Z-score is 2.5 for ACT, what is the X? Again, remember, X is mu plus Z sigma. And we use this formula, but mu and sigma come from here. 20.7 plus 2.5 times 4.3. And we want one decimal, so 4 changes to 5. 31.5 is the final answer. Again, pretty straightforward, everybody. A food marketing institute found that 35% of households spend about $150 a week on groceries. Assume the population proportion is 0.35 and a simple random sample of 300 households is selected from the population. What is the probability that the sample proportion of households spending about $150 a week on groceries is less than 0.38? We want to write the information class, the given. This is a binomial distribution with n being 300 and p being 0.35. So there are two possibilities, either 35% of household spend this much or not. That's why it's a binomial distribution and n is 300. And there are a couple of different ways to approach it. First and foremost, we want the probability of a p hat larger than 0.38 because this one is p hat. What is the probability that the sample proportion is less than 0.38? So that's what we are looking for. We're going to look at it as follows. First and foremost, NP and NQ must be larger than 10. Q is 1 minus P, which makes it 0.65. And their product is, I'm going to leave it for you to justify that 300 times 0.35 and 300 times 0.65, both are way larger than 10. So what does it mean? We can approximate it with a normal distribution. And so what is given? Mu of a p hat is a p, and sigma of p hat is square root of pq over n. You can look up the formulas that I have posted. So mu of a p hat is a p, which makes it 0.35, and sigma of a p hat is a square root of 0.35 times 0.65 divided by 300. And that results in the following number. I put, of course, a lot of decimal. And now, if you want to go with the technology, you can. Of course, we can find the z-score, or we can just stick with the technology right here. Let me show you how you do that. This is a normal CDF with the lower number, -1 E99, p hat is less than 0.38. By the way, because it's a proportion, proportion is between 0 and 1 because it's a probability. But when you go to using normal CDF, it doesn't recognize it. So even you put a negative number. But even if you put 0 here, it works. The upper limit is 0.38. Mu is 0.35. Sigma has been calculated. And this will give you the answer. Technology gives you the answer with a bunch of decimals. Here's the second method. You calculate the z-score. Z is x minus mu over sigma. And x in this case is p hat minus p over sigma of p hat. So we have 0.38 minus 0.35 over sigma of p hat, which is this number. And therefore, probability of p hat less than 0.38 is probability of a z less than this number, 1.0894. And how do you use a calculator for that? Again, lower upper is this number now. Now mu is 0, sigma is 1. And notice the answer. And if we stop at the fourth decimal, we have the same answer. The reason they are slightly different, everybody, because of the calculation of the z, this calculation, and how many decimals we go. So they are, otherwise, they would be identical. According to a survey, 10% of Americans are afraid to fly. Suppose 1,100 Americans are sampled. What is the probability percentage that 121 or more Americans in the survey are afraid to fly? I'm going to show you 3 different methods. And first we start with the binomial distribution. P is 10%, N is 1,100, because you're either afraid or you're not. There are 2 outcomes and people are independent. N is 100 and the P is 10%. So it's important to understand why it's a binomial distribution. And then recognize N as well as P. Anytime you do word problem, you have to write the given. So here's the 3 methods. First, X is 121, right? What is the probability that 121 or more? P hat is X over N, which is 121 over 1,100, or 0.11. So we want the probability of a p hat larger than or equal to 0.11. 121 or more corresponds to probability of p hat larger than or equal to 0.11. And as you recall from the previous page, the formulas are mu sub p hat is p, sigma of p hat is square root of pq over n. Mu of p hat is a p, which is 10% or 0.1. And this one is square root of 0.1 times 0.9, 1 minus that, over n, 1,100, and you take a root. So this is 0.1, and this becomes 0.0090453. I want you to understand, see, there are 2 zeros here. So keep up, put a lot of decimals. So I can go with the technology. The lower is 0.11. The upper, I want to explain the upper. Why did I put 1? Because I know it's a proportion and it shouldn't be larger than 1. Mu is this number, sigma is this number, paste it, you come up with the answer. And what I want to add here, what if I put, remember I said for the upper put 1000 when you're dealing with normal distribution. If you put 1000, it gives you the same answer. The reason is this is normal distribution. It doesn't recognize you're dealing with a proportion and this must be 1. This can only work, 1 can only work when you're dealing with binomial distribution. Here's the second method, find the z-score. The z-score, which is x minus mu over sigma, is p hat minus p over sigma of p hat. And it ends up being 1.1055465. So that's the z-score. So here's method 1. Here's method 2, probability of z larger than or equal to this number. Now this z-score can be found just the way we did it, or we can find it using the third method. So the third method gives you a different method of finding the z-score. Probability of x is larger than or equal to 121. As you recall, this is a binomial distribution. You need a 0.5 continuity correction factor. So probability of x larger than either 120.5 or 121.5. Let me quickly write both of them. I want to make sure you understand what's going on. So you either write for normal distribution, you put probability of x larger than 121.5 or larger than 120.5. Please understand, this means probability of x equals 121, 122, all the way to n, which is 1100. That's why you don't choose binomial distribution. You approximate. It's very difficult to do that. If you use 121.5, the first number larger than that, which is discrete, which is a whole number, is 122, and you miss 121 because it has equality. So you must use 120.5. So z is x minus mu over sigma. X is 120.5. What is mu? NP, 110. What is sigma? Square root of NPQ. Mu is NP or 110. Sigma is square root of NPQ or 9.94987. Plug in. And I hope you realize that this number is almost the same as this number. So this third method gives you a different method of calculating the z-score. So this SMD from here, and these two numbers are almost the same. So if you put that into a normal distribution, the lower is this number, this one or that one. The upper is 1000. Okay. Now in this case, you must put 1000. You can't say I'm going to use 1 because you're using normal. Mu is 0, sigma equals 1. And if you look at the answer, the fourth decimal is 4. Next to it is 6, goes up to 5. And they are very close, as you can see. Three different methods. Do you have to do all? No, but you need to understand the concept and choose the one that is easiest for you. Part B of the same question. What is the probability percentage that 165 or more Americans in the survey are afraid to fly? And here's the information from the previous page. The P is 10%, N is 1100. Mu of P hat or P is 0.1. Sigma of P hat is 0.009045. P hat is X over N. That means 165 over 1100 or P or 0.15. And we want probability of P hat larger than or equal to 0.15. We need to calculate the z-score. P hat minus P over sigma of P hat. P hat minus P over sigma of P hat. And so we have probability of P hat larger than or equal to 0.15 is the same as probability of Z larger than this number. And as you recall, beyond 3 standard deviations, there's really not much left. 5.5 gives you almost 0. So if you put lower is 0.15, upper is 1, mu is 0.1, and sigma is 0.00900453. Look at these two. Whether I put the upper 1 or 10,000 makes no difference because I'm dealing with P hat, okay, class? I'm not dealing with the Z. If I go with the Z, and you want to be very careful, I have to put the upper 1,000 over it. 1,000, 10,000, 100 makes no difference. Again, the reason this one works with 1 also because I'm putting the P hat values and they all result in this number. Please understand the meaning of this. This is 1.626 and it continues times 10 to the power of minus 8. This is a scientific notation. That means go to this side and count 8 decimals. This is 1 and add all those zeros. I hope you recognize this is almost 0. What is the probability percentage that 8% or less of the Americans surveyed answered they were afraid to fly, rounded to the 2 decimals? So we want the probability of P hat less than or equal to 0.08. So we are going to put it into a technology as follows. Normal CDF. Lower is 0, upper is 0.08, mu is 0.1. We get the information from here. Sigma is that. If you put the lower minus 10,000, that gives you the same answer. And since we want to 2 decimals, 1.35% is the final answer.